our next session, I would like to introduce Mahesh Jethanandani, who will be presenting API-driven network orchestration. Mahesh is a distinguished engineer at Arrcus, chair of the NETCONF working group at IETF, a Yang doctor of sorts, and is coming to us today from San Jose, California. This is Mahesh's first time presenting at NANOG, and it's a pleasure to have him speaking with us today. Please welcome Mahesh.
Thank you, Aaron, for that introduction. Morning, everyone. I guess it's sunny Seattle. Where I come from, it's always sunny. And thank you, Lynn, for that talk. By the way, I was at Cisco for almost 17 years, so I know some of that history. Reviewing some of the older presentations at NANOG, I realized that some of this is not new. In fact, some of what I'm going to present is a reiteration of talks given at NANOG 75 and NANOG 71. What is different about this talk is the state of the industry, which has changed significantly, with many more practical implementations in place. I will highlight, along with the talk, what those resources are and where you can find them. By the way, I'll be happy to take any questions at the end of the talk. To begin with, I wanted to highlight the difference between automation and orchestration. I find that G2 has done a good job of distinguishing between orchestration, something automating where orchestration is automating multiple tasks to define a process, versus automation that concentrates on a single task. That distinction is important in the management of a large network where changes are rarely ever a single task. This talk will highlight why those differences are important and how you can achieve them. Let us begin. I'll talk about the motivation behind why we need API-driven network orchestration, then talk about the protocols that can be used, the language Yang used to achieve orchestration. We can then look at the landscape of where we are in the world of Yang models. What are some of the tools that are available if someone wants to get into API development? And what some of the development resources that are available to enable that? Finally, I'll leave you with some conclusions and a reference. So, where are we with making changes in the network? Well, majority of the changes in the network still happen manually. And as you know, those changes can be error-prone. Moreover, there is no way for us to keep up with the number of devices that are coming online and the changes that have to be performed on them without at least some form of orchestration. More significantly, operators are no longer thinking point solutions. They are thinking end-to-end network management with common framework and processes that encompass not only the access, but the core and transport portions of the network. Management has been identified as the biggest area of CapEx and OpEx reduction. Some of the benefits cited are reduction in call center calls in favor of self-service portals for the customers. However, greater than 15 to 20% reduction of costs is needed to justify the move towards orchestration. Those benefits also have to be multi-layered, and that is where orchestration becomes important. Changing ever-changing customer requirements, and the ability to turn around quickly on a new service were some of the other reasons to attempt orchestration. Well, to achieve some of these cost savings, we need to move from where 60% of the effort and money is being spent on professional services and only 10% on software development, to where software development forms the bulk of the effort and money spent. Why, may you ask? For one, networking protocols have been around for a long time. Therefore, developing abstract models for some of them should be possible. Moreover, modern software lends itself to doing just that and do it in the form of small, reusable objects. Remember, the ultimate goal is not to sell a network, but to sell services on the top of the network. A combination of best current practices, whether it was from the CLI world, SNMP, or the operators themselves, that has gone into the development of the protocols that enable network to be orchestrated. As I run through the protocols and the languages used, I'll highlight what some of those best current practices are and how they lend themselves to orchestration. The first of those protocols is NetConf, or network configuration in its full form. But before I do that, let me explain where do these protocols, languages, encodings, security, and the APIs, more importantly, fit together. If you were to look at this diagram starting from the bottom, we have networking vendors, whether it's Arrcus, Cisco, Juniper, providing the devices, whether it's a switch, router, firewall, etc. The existence of multiple vendors in a network is not uncommon. In fact, it is almost desired. However, do the apps really care what device or network protocol is being used in the network? To a large extent, they do not. Therefore, the need to abstract. To manage these devices, the vendors can be asked to provide Yang models to abstract the capability of the device. Therefore, configuring something like BGP, whether it is on an Arrcus, Cisco, or a Juniper box, should be no different when using a standard Yang model. We will talk more about this in subsequent slides. Securing the transport layer are protocols such as SSH and HTTPS. The encoding of the data that these protocols carry come in the form of XML, JSON, or some form of binary encoding. The protocols used in the transport, of course, are NetConf, RESTconf, and now gRPC. Exposing northbound is a set of APIs that apps can then call to realize the orchestration of the services. These APIs is what I'm referring to in the title of the talk. So back in 2000, I think more like 2003 or 4, ITF had a meeting of minds of vendors and operators to gather requirements for what would form the next network management protocol. The first requirement that operators came up with was that there be a distinction between what is configured on the box and what the state of that configuration would be on the box. The second requirement was that even between configuration, distinction be drawn between what was the next planned configuration in the form of candidate config, what was currently running on the box, which is the running config, and what was the box going to boot off, and of course, the operational state of the configuration. Another requirement in that workshop was that the configuration be validated before it is applied. And when it is applied, that it should be done in the form of a transaction. That is, either all of the transaction or none of the transaction happens. More on this in the next slide. When fetching configuration or operational data, the operators wanted a way to filter the data to what was needed instead of it being sent the entire data. That the management protocol allows for the data to be streamed out of the box instead of having to be pulled for it. As you will notice, NetConf provides some of those basic constructs that operators wanted and are needed to orchestrate network services. Most of you here who are familiar with databases are familiar with the key properties of a transaction, the so-called acid test. The ability of any transaction to meet the acid test and the SQL language is what enabled the boom in the database industry. The most important aspect of that development was that applications actually got reliable. So when a transaction happened, it really meant it had happened. NetConf makes the network a distributed database where every change in the network has to stand up to that particular acid test. Let me quickly touch on RESTConf because of wide adoption of REST interfaces. Those familiar with REST and REST APIs particularly like RESTConf for its lightweight approach to NetConf data stores, combined with leveraging well-known encodings such as XML and JSON. It provides for most of the CRUD operations that NetConf provides, but over HTTP. However, it's not meant to be a replacement for NetConf. RESTConf utilizes post, patch, put, get, delete, and update as part of the CRUD operations. The configuration and operational data of the devices is exposed as resources to a client. Well, we have talked about protocols, but what about the payload that is carried in as data in the protocols itself? The payload is defined by the data modeling language Yang that defines the schema of the data, much like schemas did for databases. Yang is a data modeling language, the emphasis being on data modeling, not information modeling, something UML does. It describes exactly what data to expect and its type. In other words, the schema. Other than being easy to read, it forms a tree-like structure with its hierarchical nature which is easy to follow. It is extensible, therefore you do not have to have everything defined day one. It can be augmented as new capabilities need to be added. It has well-defined constraints that it places on configuration, that it models by using must and if statements. And it maintains a well-defined versioning scheme for backward and forward compatibility. Well, you might hear a lot about different types of Yang models. I like to divide them into three categories. Service level models that model end-to-end services, and those models have no concept of a device or the technology that is being used to realize the service. An example of service models are those that include E-line, E-LAN, or E3 services that have been defined by MEF in their document MEF 58. These service level models are also known as Ligaro models. Infra level models are models that are used to define infrastructure. An example of an infra model is a topology model, something that is used to define how the different devices interconnect. These models are commonly referred to as Presto models. Finally, there are the device-level models that define the capability of the device and were referred to in the earlier slide. They are commonly referred to as Adagio models. So, what does the landscape of the Yang models look like today? Well, we have seen an explosion in the definition of models by different entities in the industry. They can be broadly classified as standards body models. The bulk of those models have been put out by IETF, and they're available as in individual RFCs or in the GitHub location that I point to in this slide. But IETF is not the only standards body involved in modeling. We have BBF, IEEE, HC, INA, and MEF that have put out their own Yang models that complement the IETF model. Then there are the operator-driven and defined set of models. They generally have had limited input from outside the tight-knit group of operators, although they have started to take some input from vendors. More importantly, they are not aligned with the Yang models from the standards development organizations. Well, what is the implication of that? As an operator, or even as a vendor, one has to decide which set of models to choose from. A good way to look at is to look at your current set of requirements of services from a feature perspective and decide which models align with your requirements, and insist that vendors support it if they do not already. The vendor models are augmentations of the industry-wide Yang models, either from the bucket of IETF and other standards bodies or operator-driven models such as OpenConfig. The vendor models are there because they extend the capabilities that were missing in the industry models. For example, BGP configuration for VPN services is something that's missing in OpenConfig. In some cases, the vendor models were there to support the particular vendor's CLI that predates the Yang models. Again, note that one vendor models are not necessarily compatible with another vendor models, but that generally tends to be a smaller subset and is specifically for vendor-specific feature or capability. So, what are the publicly available tools to play around with these protocols and models that we have been talking about? There's Pyang that is used to validate and build the tree that I've been referring to of the models. Trees are an easy way to understand the hierarchy of the data. LibYang, another tool, is a great way to validate examples containing instance data of that configuration. And of course, using the Yang models, one can validate that instance data. Here are some client tools that you can use to play and run example changes through before using API to encode them. Some of these tools are standalone tools, while others, like curl, work much like a browser does and can be used inside a program. I particularly like Postman and have made available some Postman collections of common commands that you might run on the CLI. Examples include getting interface counters or BGP neighbor state. Once an example works in Postman, I generally use Python to code it up. However, if you're looking for a GUI tool to play around with instead of these CLI tools, you can use OpenDaylight that auto-generates RESTconf APIs from the Yang models that the vendor provides. and something that it reads from the device directly, so you don't even have to give it. It has also an API docs feature that lets you explore local and the models that it has loaded from the device, and lists not only the syntax, but also the arguments that it expects. If you're looking for a commercial orchestrator, there is one from Cisco, the Network Service Orchestrator. Having looked at the tools, you might be wondering, where do I find some of the development resources? A good place to start is NAPALM. It is a publicly available Python 3 library with support for multiple vendors, including Arrcus. However, it is template-based. Well, what does that mean? Instead of programming individual nodes that you would normally do with APIs, you are modifying and writing templates. Those templates can then carry the parameters that you want modified across services. Think shell scripts that take input parameters. To be able to use APIs to enable orchestration, you need good API documentation. And something that I forgot in the set of tools is another tool called Yanger that enables you to do just that. It takes a Yang model and actually generates API documentation for you in case one is not available. Yang has therefore focused on readability and automatic generation of API documents from those models. A Swagger editor reads these auto-generated files, giving you not only clear examples in curl or an HTTP request that you can put in a browser, it even allows you to play with those APIs and see possible return data and return codes, whether it is 204 for success or 4XX for failure. Once you have played around with these tools and the model itself and are ready to jump into programming with the Yang models, you can use the tools that I list to generate bindings for whether it is in C++ or Python, leaving only the logic portion of the code to be written up by you. In conclusion, I say that we have reached a critical set of models that are needed and available in the industry today to enable orchestration. By moving towards a model-first approach, we see that vendors are able to provide a consistent CLI and API to you to provide towards management of the device. That programmable approach can start with templates that we talked about in NAPALM, and then move towards a true API-driven approach. Network orchestration is where databases were almost 30 years ago, and with its transaction approach can achieve a reliable way to manage changes in the network. That approach can then enable new services that can be deployed in minutes, if not days, and certainly not months. For further reading and exploration, I wanted to leave you with this one reference that you can start. I'll open the floor at this time for any questions that you might have. Thank you.